Good afternoon, welcome. So, this is now entering lecture 34 and as always let me begin by going over what we covered last time. So, last time the title was Belief Propagation Decoding Continued, and in reality this was the lecture in which we actually started talking about belief propagation. And the perspective I wanted to bring in the last lecture was that as far as decoding is concerned, the algorithm, the belief propagation decoding algorithm is exactly the algorithm that we used in conjunction with the GDL. So, that is for that reason, just to remind you that that was the case, and also to make another point that we when we use the GDL to decode the 742 block code, then I wanted to point out that there was a simple interpretation for every message that was passed on the junction tree graph for that particular code, and it had an interpretation in terms of beliefs, and in fact it is that which actually gives rise to the term belief propagation decoding. So, that is how I actually started out. So, here what I pointed out was, look, if you actually look at this figure over here, then you can see that you have messages. Let us say that we are interested in decoding the value of this particular code symbol, and then I tried to give you a sense for. So, overall what we are interested in is finding out what is the probability that x1 was transmitted giving all the received symbols, and given that the code symbols themselves satisfied parity checks A, B and C. So, this in itself is a belief, because it is the belief about x1 based on all the evidence. But over and above that, it was interesting that you can also give interpretations to messages, intermediate messages that also have can be explained in terms of beliefs. So, for example, when you come down over here, then the message that was passed here, now again we are aiming to eventually compute the objective function here, but even at this intermediate step, the message that was going across this barrier over here was the current belief about x4 based on some evidence. What does some mean? Well, it is all the evidence which is on this side of the barrier, and more specifically that evidence is, well, the received symbols y3, y4, y5, y6, y7, and on top of that we also have the belief, we also had knowledge of the particular parity checks B and C. Then rolling back even further, if you actually look at the message across this barrier, again it is a belief about x4, but this time based upon y3, y6 and the parity. Okay. So, when we talk about belief propagation decoding on the Tanner graph, then we are doing exactly this method of message passing. It is exactly this way of passing messages that we actually carry over. The other question that is in your mind is, well, but you know, this whole theory was actually developed for junction trees, whereas suddenly you are importing it now to the Tanner graph of an LDPC code. What is the connection? And then I actually pointed out that, wait a minute, if you assume, so here is your Tanner graph, if you assume that the Tanner graph of an LDPC code has a tree like neighborhood to depth 2L, and what you mean by that is that if you unravel the tree like this, and this is called a computational tree, then every node that you encounter is distinct. So, that means there are no cycles. For example, if this node 4 were to also appear here, that means there would be a cycle in this graph, right. So, since the nodes are all distinct, at least to depth 1, 2, 3, 4 times 2, 8, to depth 8 there are no cycles in the neighborhood of node 21. Okay. So, when the neighborhood is cycle free, then I made the point that, look, if you actually write down these parity checks the way we did for the 742 code in terms of listing all the variable indices that they actually check parity on, then you see that in fact it is a junction tree. For example, and the way you check for a junction tree is just by projection, right. So, let us project it, for instance, on variable 17. So, if you project onto 17, then you get actually a connected graph which consisting of these 4 nodes. So, similarly you will see that in every instance you get a connected tree, and therefore, this is a junction tree. All right. So, this is the junction tree that one would obtain if one posed the problem of computing this as an MPF problem. Okay. So, we are in fact under the tree like assumption in the setting of a GDL and of the junction tree, and because of this we can actually interpret every message that is being passed around in the graph as a belief. For example, here you would be passing from this node to this node a belief about x17 based on the evidence corresponding to received symbols 1, 2, 3, 4, and including the knowledge that there was a parity check here and a parity check there. Okay. So now that is why it is called belief propagation decoding. I introduced the notation of E1, E0, EdV minus 1. So, this stands for evidence. So, at a generic variable node, you get some belief about xt from the channel, which I call evidence E0, but then you also get evidence from the other check nodes, which I call E1 to EdV minus 1. And what actually goes out is your belief about xt based on the union of all this evidence. Okay. So, that is actually listed here. And more precisely, in terms of the GDL, we know that these because of the way GDL passes messages, because at a variable node the GDL would just collect all the incoming messages, multiply them together and send them out. Okay. So, that is what we are doing here, and this proportionality is included because well, for reasons that we have seen earlier. Okay. Now we are going to do something slightly different from what we did under belief propagation, because we are going to actually interpret rewrite these messages in terms of log likelihood ratios. So, in particular here, whereas this is a belief, we are now going to pass on to the ratio of beliefs which is the likelihood ratio, and then the moment you pass to ratios, that is, we evaluate this. Remember that under belief propagation we are passing, or GDL, we are passing functions, but now we are evaluating the function at a particular value of xt, 1 and minus 1 in this case. So, when you compute the ratio, this proportionality constant goes away and we are left with an equality. Okay. So, we have a likelihood ratio here on the left, which is the product of the likelihood ratios. So, then we pass on, then we take logs on both sides, and that leads us to the simple expression that the log likelihood ratio at the outcome is simply the sum of the log likelihood ratios at the input. Okay. So, very clean and simple. So, the next question is, well, what happens at a check node? Well, things at a check node are slightly more involved, because there is a marginalization that actually takes place. So, if you will recall, at a check node what actually happens is these are in fact the incoming messages, very similar to the types of messages that are incident on a variable node. What goes out is also very similar, but the relationship between input and output is like this, because of the marginalization here, because if you think of this as the GDL, this check node is really a function of several variables, right. So, the local domain in the terminology of a junction tree would list all the variables. Now, on the other hand, you are sending a message to a variable node that has a single variable, and therefore, the local domain consisting of a single variable. So, between here and here you need to marginalize with respect to all of the other variables. So, that is the expression over here. Now, once again, just as we did in the case of a variable node, what we would like to do is we would like to rewrite this in terms of log likelihood ratios. So, how can we do that? Well, so there is a technicality here. So, we go through some manipulations which I will not repeat here, but when all is said and done, what you actually get is this relationship between input and output. You get that the log likelihood ratios at the output are related to the log likelihood ratios at the input like this. Okay. So, this is where we will actually pick up our lecture from. So, because I have gone through this in some detail, I am not going to put down a summary, but I am just going to jump or maybe I will just very quickly and briefly summarize what we did. So, the recap in today's lecture of the last lecture was a discussion of belief propagation decoding of LDPC codes, okay, and particularly and relation to message passing along junction trees along a junction tree. And then we expressed messages, or rather messages, and in brackets I will write beliefs expressed in terms of log likelihood ratios. Okay. So, that is the summary, and now we want to pick up the thread in today's lecture. Now, today's lecture is going to actually talk about something called density evolution, in which is really similar to what we did in the case of Gallagher's decoding algorithm A. There what we did was I outlined what the decoding algorithm was, and then I tried, as far as performance analysis was concerned, we were interested in trying to actually characterize, well, if you were to run this algorithm, what is its performance in terms of the number of erroneous messages that are passed. So, we want to do something very similar even here. Okay. So, because the calculations tend to get a little bit messy, what I thought I would do in this lecture was actually pre-write the calculation. So, I have pre-written the lecture, and I realized that when you pre-write a lecture, the lecture tends to go a little bit fast. I will try to slow down a little bit to compensate. Okay. But here, just to recap, so at a variable node we drew the conclusion that beliefs the equivalent message passing rule in terms of log likelihood ratios at a variable node is simply to take the sum of the incoming log likelihood ratios, including the one that comes in from the channel. At a check node, okay, now at a check node, although it was not obvious, it is clear, and I will just perhaps put this down in your last lecture itself. From this it follows that therefore, tan hyperbolic LDC by 2 is the product j is equal to 1 to DC minus 1 tan hyperbolic Lj over 2. Okay. So, that was at the tail end of last time's lecture. So, we pick up the thread here. So, we know that the input output ratio at a check node is in terms of the tan hyperbolic function, all right. So, the incoming are the LIs, the outgoing is LDC. So, you can convert this and say that LDC is therefore twice the inverse tan hyperbolic function of the product. Okay. So, this describes the input output relationship. So, once you know this, you already know how to actually decode, because you know the messages that are going back and forth. I have told you how messages are passed across a variable node and a check node, and you are done. But now we want to start performance analysis. So, maybe just to actually emphasize that, let me just insert a page and just say, just add a note saying, with this we are done with the description of belief propagation based message passing decoding of LDPC codes. We now turn our attention to performance analysis. Okay. And the performance analysis will be carried out in terms of it will be carried out via density evolution. So, this is to be carried out using density evolution. Okay, so what does that mean? It means that so perhaps I should just say that maybe I should pause to illustrate that a little bit. So, what we mean by that is, let us say that you have a variable node here, okay, and you have incoming and outgoing messages L naught, L1, L1, LDV minus 1 and LDV is your outgoing message. And similarly at a check node, and similarly at a check node you have incoming, outgoing messages which are expressed in terms of log likelihood ratios. And remember that any log likelihood ratio, so let us say this one LDV is Ln of P of some variable x t equal to 1 given some evidence divided by P of x t equals minus 1 given certain evidence. Now, when we do performance analysis, we assume that the all one code word was transmitted. So, put that down here. In carrying out performance analysis, we assume that the all1 code word was transmitted. Now we discussed this sometime earlier when the issue of, well, in general when you are doing performance analysis of LDPC codes, we said that look, you can always assume that the all1 code word was transmitted provided you had certain conditions that were met. That is, you needed the channel symmetry condition to be met, and you needed that there was symmetry in the messages passed across a variable node, and you needed symmetry in the messages that were passed across a check node. And in fact, you can check that that is very easily the case, because here, so let us take a look at that. Okay. So at a variable node, you have that the output message is simply the sum of the incoming messages. Variable node symmetry requires that if you change the sign of all your incoming messages, the output will also change sign, but that is clearly the case here. Okay. So let us just make a note of that by saying that, so I will remove this one here, create a little bit space and put down that note that the variable node symmetry condition is met. Right. So, the variable node symmetry condition is met. At a check node, what we have is that the input output relationship is in terms of the tan hyperbolic, and at check node, the check node symmetry condition that we actually required was that if you put a sign on each of the incoming messages, then the sign on the output should be the product of the incoming signs. Okay. Let me see if I can actually pull that up. Okay. So, remember these are the at a variable node, we said that if you multiply all the messages by a constant b, which is either plus or minus 1, then the output would also be multiplied, and we just checked that that was true for the case of belief message passing based on beliefs. At a check node, you need that if the incoming messages are signed with individual signs, then the outgoing message is signed with the product of the signs. And I just want to actually show you that that is the case here. Well, why is that? Because supposing each of these incoming messages was multiplied by some b, okay, then the nature of the tan hyperbolic function causes them to be pulled out of this, and then again the inverse is similar. Okay, why is that? Well, take a look at the tan hyperbolic function, which I have actually sketched, which you will see sketched a little bit later here. Here is a sketch of the tan hyperbolic function. So, you see that the tan hyperbolic function has the same size as the input, and in fact, if the input reverses sign, by symmetry the tan hyperbolic also reverses sign. So, what that means in particular over here is, so perhaps I will just insert a page here. And say that, so can verify that LDC, that if you replace each Lj by Lj times Bj by a sign, where Bj is either plus or minus 1, then LDC, the result, then LDC is equal to twice tan hyperbolic inverse the product you can verify that it first of all pulls out here and eventually pulls out of this. So, you actually get this. And you get okay, and hence the check node symmetry condition is also met. Okay. So, coming down here, so we are now with that we have justified in making the assumption in carrying out performance analysis that the all one code word was actually transmitted. So, that is where we are now. So, we want to do belief propagation decoding, and the way you do belief propagation decoding is actually say, you know what, every time I pass a message from a variable to a check node, I am going to regard the message. See, because this is an iterative process, it is an iterative process that is actually carried out on the Tanner graph. Okay, here is the Tanner graph, and in belief propagation decoding what we are doing is we are passing messages back and forth along these edges, and each of this is a log likelihood ratio. Now, we will say that a message is incorrect, and we know that all the code symbols can be assumed for performance analysis to be assumed to be all 1. So, and if your belief is correct, then since your belief is the log likelihood ratio over here, okay, if you look over here, if in fact this is positive, that means the probability that it is a 1 given E is greater than the probability that it is minus 1, which means that this quantity is greater than 0, right. So, if this quantity is greater than 0, then you are going to conclude that, well, my current belief is that it is actually a 1, that 1 wins over a minus 1. Okay. So, in this sense we are going to look at these messages and look at the sign of these messages. If the sign of the messages is positive, then we are going to say that that is a correct message. If the sign is negative, we will actually say it is an incorrect message. But how do we actually analyze how many or what is the probability with which they are incorrect or correct? So, what we are going to do instead is, well, we will actually try to do something more because it is easier. We will not only examine the sign of these messages, we will actually examine their density function. So, now our interest is in saying, well, we actually want to see, so let me duplicate this slide and I will put some writing on it. Okay. So, let me get rid of some superfluous writing here. So, this time what we are going to be interested in knowing is not on just the likelihood ratios, but rather on their densities. So, we are going to be interested in saying, well, look, there is an L naught here, that is true, but it has a certain density function. There is an L1 here and there is an associated density function. Okay. And similarly, over here there is an L2 and there is a P of L2. Okay. And at the output I have an L dV which is associated with a certain L dV. And so, what we are saying under density evolution is that earlier we were worried about the messages, now we are worried about their density functions. So, knowing the relationship between this variable and these other variables, we want to translate our knowledge of that relationship to actually derive these densities in terms of these other densities. Okay. By the way, I am kind of using short form because normally what you do is you would write P x of x, but I am just writing P of x, saying that the underlying random variable is understood. Okay. So, hopefully that is actually clear, that is just short form notation. All right. And the same thing here, that is you have an L1 here associated with the PL1 and so on. Okay. So, that is our next task, is to actually compute density functions, and I just wanted to introduce some let us do one thing. Let me get rid of this page first. Okay. Here we go. So, we will actually do a few manipulations before we get to the density evolution stage. So, okay. So, I want to slightly change the order in which I carry out this description. So, let me just skip ahead and go over here and so let us start the discussion at a variable node. And at a variable node we know okay, that's okay. So, I take that back. So, I see that my my pages are in a certain order. So, rather than confuse you, let me describe them in the order in which they are. So, let us get back here. So, we were talking about carrying out density evolution, which says let us describe the densities in terms of the incoming densities. But before that, there are some computations that will be found helpful. So, I am going to request your patience, because right now it is not completely motivated, but we know that what happens in terms of the messages is that here the likelihood ratio is simply the sum of the incoming likelihood ratios. Here it is a little bit more complicated, because you have that your LDC, the incoming and outgoing likelihood relationship is through the tan hyperbolic, and that presents some challenges. So, we would like to overcome them, and we will actually do a change of variables. What we will do is we will replace the tan hyperbolic function by a pair of variables. So, x will actually keep track of the sine of tan hyperbolic of L by 2, but because the tan hyperbolic function is monotonic in L and sine preserving, the sine of the tan hyperbolic is the same as the sine of L. The second is to keep track of the magnitude of tan hyperbolic, and we will keep track of it by making use of the log function, and it will be convenient to take the negative log. Okay. But basically what we are trying to do is we are trying to say the reason for this is we are going to say, look, at a variable node we have this very simple relationship, okay, in terms of log likelihood ratios. Here it is more complicated. The relationship is in terms of the tan hyperbolic. So, the first thought that comes to my mind is, well, why don't you take logs on both sides, then it will become an addition again. The only problem with taking logs on both sides is that this is a quantity that could be either negative or positive. So, you can't take the log of this, because when it is negative it is not even defined. So, we get around that by saying, well, let us split this into two variables or two functions, one function which carries the sign information and a second function which carries the magnitude. So, that is what is actually happening here. So, where x keeps track of the sign and y keeps track of the magnitude. So, then our original relationship in terms of the type of tan hyperbolic you can show that it simply replaced to saying that, look, the sign at the output is so this should be x dc and y dc. Let me correct that. This is x dc y dc. So, that is the output x and y's are related to the input x and y's simply by summation. Okay. And that is not hard to see, because each of these is the log of the magnitude. So, since the magnitudes are multiplied, the logs are added. So, that is why you have this relationship. And similarly, the sign you can also verify that this is true, because each of the x's is keeping track of the signs of the individual tan hyperbolic, and the sign of the overall is in terms of the product of the signs. Okay. But here what x dc is doing is it is keeping track of the sign. So, okay, so the question boils down to, what do you mean by the sign function? So, the sign function is defined in a somewhat unconventional way. So, where sine of L is 1 is 0 for L greater than or equal to 0 and is 1 for L less than 0. That is the sign of so if you were to plot this, it would look like this. It would be something that is 1 in the negative part, and then it would be 0 for the positive part. So, here I am plotting sine of L versus L. Now, what we conventionally think of as the sign might be, or is rather, is what is minus 1 to the power sine of L, because this function is more like the function we would have in mind, that is, it is 1 here and it is minus 1 for negative, right. But however, it is convenient. So, this is a binary 0 1 function here, and this is our traditional plus minus 1, but it will be found more convenient to work in terms of this. Okay. So that's the reason why, whereas in the plus minus 1 domain you'd simply have a multiplication of the signs, in the 0 1 domain it turns out to be an addition. And the nice thing about it is now that we have addition on both sides. On both terms we actually have addition, although one addition is modulo 2 and one is this. Alright. And this is just saying, okay, here's L tan hyperbolic. When you take the log, you get a function that looks like this. When you take the negative log, it looks like this. Okay. The sign is this function. So then if you want to represent now in terms of this transformation what is taking place at a check node, you see that you have the incoming log likelihood ratios. Then there is this transformation T which takes an L to an X and a Y, exactly like was actually shown here. That is, given an L, you pass to an X and a Y using this mapping. Okay. So that's where this transformation is actually carried out. Similarly, on each of the incoming messages, you transform the corresponding log likelihood ratio into a pair of functions, one representing the sign and one representing the magnitude. And then this check node simply has to actually compute the sum according to this expression over here. So it's just going to compute the sum here. And then after you computed, so xdc is the modulo 2 sum of the incoming xj's, ydc is the real sum of the incoming yj's. And then you do an inverse transformation which takes you back from here to here. Okay. So we've made this change in the check node from this other picture here, because the picture here involved the tan hyperbolic function and we wanted to get rid of that. Okay. So we have this. Now density evolution says that, look, in abstract it says that, look, whereas earlier we acknowledged that at every variable node you had a map, in the initial iteration, that is in the 0th iteration, when the only input is from the channel, the map is from the channel output alphabet to your message alphabet. And associated to that, because any time you have a map from one variable to another, you also map the density function on that variable to a density function on this random variable. Okay. So this is the corresponding map in terms of the density function. The distinction between this and this is the presence of this star. So we are saying that this mapping here induces this mapping on the density functions. Similarly, at the lth iteration there is, and you can see that here, in terms of messages there is a mapping from the channel output alphabet and the message input alphabet to the output message alphabet, and which is what this is. There are dv minus 1 incoming messages. So we assume that the message alphabet along any edge is the same, but the channel output alphabet could be distinct. So this is the mapping that is carried out at a variable node, and the corresponding mapping in terms of density functions is given by this. So we put the star. The only thing is that you see that I actually in taking the mapping on the density functions, I actually have a product of density functions here, and that should be some, we need to pause there, because I mean, how are you justified in taking the product? That seems to imply that your incoming variables are linear, are statistically independent, and that is the case, because you see your output here is the sum of these input variables, but if you assume that the neighborhood is tree like, right, that means that if you unravel the Tanner graph you will get a graph like this. What we want to point out is that, look, the message that's being passed, the message that's, for instance, that's being passed here, okay, and the message that's being passed here, this message is now a function of all these received variables. This message, which is the likelihood ratio. So this is, for instance, this could be an L1, this could be an L2, and what actually goes out is an L dV. There is also a channel input, okay, which is an L0. So, now each of these inputs, so L0 is a function only of the corresponding received symbol. So, that is Y21. L1 is a function of all these received symbols, and it also makes use of the fact that there are certain parity conditions that the code symbols satisfy. L2 corresponds to this branch of the tree and therefore uses these received symbols knowledge as well as these parity checks. Since the received symbols are independent given the transmitted code word, these messages are independent. So, that is important. So, the incoming messages under the tree like assumption can be assumed to be independent, and this is the reason why you actually write the product density function, why you write it in terms of the product of the density functions rather than a joint density function. Similarly, at a check node, the messages are mapped from a DC-1 fold messages, and this is the corresponding message on the map on the density functions. Okay. So, now so we want to actually say that look, now we are getting down to specifics. We know the input output relationship in terms of messages is given by this. What can you say about the densities? So, the trick is to actually work with a characteristic function. So, we take the characteristic function here, and because these are independent, this expression breaks down into the product of individual characteristic functions, but any characteristic function is more or less the Fourier transform apart from a sign. So, in fact, let us in order to make it exactly the Fourier transform, let us simply put a negative sign on both sides. Okay. So, then the characteristic function as defined in this manner is the product of these, okay, by independence, and each of these is a Fourier transform. So, what that means is that the density function of the output message can be obtained by taking the Fourier transforms of the incoming density functions, multiplying them together, but by symmetry they are all actually identical. So, you can raise it to this power, then you take the Fourier inverse. Okay. So, that with this we have actually accomplished density evolution at a variable node, that is we are able to relate the density function of the output message to the density functions at the input. So, that was relatively painless. At a check node things are a little bit more complicated. Why is that? Because now your check node looks like this. The mapping at a check node is in fact a series of mappings. First of all, each of the individual messages is passed across a transformation T, and then thereafter, after the check node carries out its map, then there is an inverse transformation. So, in some sense you have to actually trace the evolution of the density as it goes across a transformation. So, that is step 1, across the check node, that is step 2, and then across the reverse transformation. So, we now have to keep track of 3 transformations of the density, okay, and that is what we will actually do. So, first step, there is the incoming density, incoming log likelihood ratio is transformed from an L to an X and a Y, and you can show that if you are given the density function of L, then the joint density function of X and Y is given through this pair of expressions. Why does it look like this? Because X is a discrete random variable, Y is continuous. So, X can take on values either 0 or 1, whereas Y being continuous. So, we break this joint distribution function into 2 parts, one which corresponds to x equal to 0 and one which corresponds to x equal to 1, and we get these expressions. Okay. So, this involves some change of variables transformations, which I will not discuss in any great detail here. Okay. Now, so what has that accomplished? That has accomplished that means that we now know how to actually go from a density here given here to a density on the x1 y1. Now, we want to go, given all the incoming densities on xy, to the density on the outgoing xy. Okay, so, let us do that next. So here let us define a joint characteristic function of x and y in this manner. So so it is -1 to the lambda xj e to the minus syj, where lambda takes on values either 0 or 1. S you can think of as a complex variable, as you would in the case of say a Laplace transform. So this can be evaluated by actually evaluating it. Now this expectation is over both x and y. So x can take on values 0 and 1 and y takes on a continuum of values. So this expectation evaluates to this, okay. And so it is an average, so it is an average over all the values of x, but there is only 2 of them, and an average over all the values of y, and that is a continuum. So that is why you have a sum and an integral. And you can actually see that if you separate the parts corresponding to x equal to 0 and x equal to 1, that one term is the Laplace transform of p0y excuse me, and the second is the Laplace transform of p1y, okay. And then there is a -1 to the lambda which separates these two terms. Now since the Lj and hence the xj yj are statistically independent, okay, so now I am going back over here to, okay, at the output we can do the same thing, and because x dc, so now recall that x dc is equal to the sum of xj mod 2, y dc is the sum of yj. So keeping this in mind, here it follows that you write this out, and again by independence this breaks down into the product of the individual joint characteristic functions. So what this is telling us is the way you can actually, so let me go back to the perspective picture here, which is this one. So now we are trying to go from the density functions on the messages that are coming here to here, and what we are saying is you can go from these density functions to this as follows. You can go from the joint density function, you can evaluate the characteristic function and the set for all the inputs, then by multiplying them in this way you can actually go to the joint characteristic function at the output, from which you can actually take the inverse. I mean, you can go from a joint density function to the joint characteristic function, but you can also go backwards. So how do you actually go backwards? Well, if you are given the joint characteristic function, then you are given this expression over here, okay. You evaluate this for lambda equal to 0 and 1, and in terms of these transforms you can actually show that you can recover p x dc y dc 0y by taking the Laplace inverse of the sum divided by 2, and p of x dc y dc 1y by taking the Laplace inverse of the difference, okay. So in this way you can actually, so that means that now we know how to go so now we know how to go from a density function here to the density function here using joint characteristic function. It remains to go across this transformation, okay. So and here is the inverse transformation. So we are given these x and y, density function of x y, and we need to find the density function of L. Again, using this particular nature of this transformation, you can actually show that the density function at the output is related to the joint density functions like this, okay. So with that we have actually completed the entire density evolution, because we were able to relate at a variable node the incoming densities to the outgoing density. Check node we had to work a little bit harder, we had to work in 3 steps. We could do this at one shot, but here we needed to work in 3 steps: a step at B, a step at C, and a step at D. We had to do density, a transformation of densities across T, and then we had to do the joint characteristic function to derive the density function here, and then do a transformation of densities corresponding to T inverse in here. But with the net result that once you apply this, you can actually keep track of the density functions at either a check node or a variable node. Okay. And that basically is how you do density evolution when you are doing belief propagation decoding. So, I think our timing has been very good. I have got just under a minute left. To summarize, what we did today was we followed up on our earlier discussion on how belief propagation is carried out, and we went to the harder task of actually saying, well, now how do we analyze its performance. So, we want to keep track of the likelihood that it is going to make errors, which the one method that people know is to actually do this by keeping track of the density function of the messages that we are actually transmitting, and this is computationally a little bit messy. So, I tried to take you quickly through that. The details are in the write up, but admittedly it was a little fast. So, I will let you pore over this on your own, and we will stop and continue next time. Okay. Thank you.